Welcome to clickmyproject.com. Our product title is Optimized Active Single Miller Capacitor Compensation with inner half feed forward stage for very high load 3-stage OTAs. Let us see about abstract of our product. In this proposed implementation design is a new effective single Miller capacitor compensation topology for 3-stage amplifiers with very large capacitive loads realized through an active feedback capacitors together with an inner half feed forward stage. The main advantages of the proposed 3-stage amplifiers are the enhanced unity gain bandwidth and the reduced silicon area, and small signal analysis are performed and the design equations are obtained in the process. In the proposed technique, only one Miller capacitor in series with a current buffer is utilized. Moreover, an optimized design strategy which profitably exploits the two left of plane zeros is presented in the overall process. To improve the amplifier large signal transient response, the topology also includes an external feed forward path that only marginally affect the frequency compensation, and a novel slew rate enhancer section is included in the process. To validate the solutions, and a 3-stage OTA driving a 10 nanofarad load has been designed and implemented in a standard 0.35 micro-ohm CMOS technology. Next we see about flow diagram of our product. In this flow diagram, first input signal is fed into a first stage of operational transconduction amplifier. Operational transconduction amplifier is nothing but is an amplifier whose differential input voltage produces an output current. Thus it is a voltage controlled current sources. There is usually an additional input for a current to control the amplifier conductance. The OTA is similar to a standard operational amplifier in that it has a high impedance differential input stage and that it may be used with negative feedback, and the output of the first stage is fed into the second operational transconductance amplifier stage. After that, that output is fed into third OTA stage. Finally, that is fed into the capacitor and SRE block. In between the third stage and capacitor SRE block, the output signal will be taken from that. And the next one, the important block is active single Miller capacitor compensation. Nested Miller compensation is not suitable for large capacitive loads in lower power operation, primarily due to the degradation in bandwidth resulting from an increased number of stages. The size of compensation capacitors also increase proportionally with the load capacitor and hence is not suitable for higher integration. These drawbacks led to other compensation schemes such as multi-path nested Miller compensation. This scheme introduced a feed forward path for high frequencies that improve the bandwidth of the overall amplifier by pole zero cancellation within the pass band. Stability of the NMC is improved by removing the right of plane zero. To this end, phase compensation schemes such as nested compensation. This technique uses feed forward paths to extend the bandwidth, but it is not suitable for large capacitive loads and low power applications. The active filter compensation technique uses an active capacitor to replace a passive one, resulting in smaller capacitor size. It also uses a high speed block with a feed forward path to enhance the bandwidth and the transient response of the amplifier. Next we see about running process of our product. In this proposed implementation is done in Tanner EDA tool and SEdit tool. First open the SEdit window and create a new file. After creating that, we open the new cell. In the new cell we create a name for that. After creating that, we include the library files for corresponding and the time values in the simulation parameters. After including that, we draw the circuit diagram as per the base paper. After arranging that, we click the run symbol, then output will be displayed in the T-Spice window. First one, the T-Spice window will be open. In the T-Spice window, the system time delay and overall elements data will be given, and in the T-Space window also used to calculate the power and time delay for corresponding used input and output data. These are the corresponding PMOS and NMOS for using in the circuit. After that, we click the run symbol. The output window will be open in the waveform format. That is a W-edit window. In the W-edit window, the input and output data are given. Here, this is the input and output data. So this is a normal way. Then click the expanded chart. Then the output will be displayed in this manner. After clicking that, we want to see the frequency values and the FFT analysis. Then click the FFT value, then corresponding input data and output data frequency and voltage in dp values are given. And also next one is the power output for corresponding input and output data. This is the power output. So this is the power value. The value is range is milliwatts. So this range is around 1 milliwatts. So this is the corresponding input and output data. So these data will be shown in the waveform format. If you want to show the frequency value, then click the FFT analysis. The corresponding waveform will be displayed. And another one, the time delay will be calculated in the T-Space window for given calculation. Then that values are stored in the notepad and the corresponding folder. This is the time delay value. In the corresponding, the time delay is 2.00 e power minus 11. So the overall time delay will be reduced and also power consumption will be reduced. Thank you for watching this video.